Hey y'all, how you doing? Hope you're having a great day. Today we're going to finish up our discussion on how light absorption occurs, and this is the third part to a three-part series. And in this part we're talking about the driven, damped harmonic oscillator, which is the most general harmonic oscillator you can get. Now, in the previous video, in part 2, we imagined a damp harmonic oscillator, and before that we just imagined the simple harmonic oscillator without any damping. And we're imagining applying an electric field to a neutral part of space that actually contained two overlapping charges. But applying that electric field would separate those charges, it would induce a dipole, and then we imagined just shutting off that electric field, and once that's shut off, these charges are going to want to come back together in a certain amount of time, and they're going to oscillate in time like such. So T1 would be time 1, time 2, 3, so on and so forth. So this is the general equation that we had for the damped harmonic oscillator, and this was the most interesting general solution. This was the underdamped harmonic oscillator. There was 3 cases, but this was the most interesting and probably the most encountered one. And if you plot this, it looks something like this. So C is a constant, and then this exponential decay part is an exponential envelope that the wave stays inside, and there's a cosine part with this omega, which I messed up in the last video. Omega was equal to this, because we had the square root of some stuff inside. It was 4k minus gamma squared over 2m, and we had 3 different cases depending on what the inside of the square root looked like, and this was our last case. So our omega was equal to this. I might be wrong by a factor of 2 though. And then our phi was just some phase shift. So a cosine would normally show up. Its highest point would be at the origin, but this is a little bit shifted. Okay, so that was just a little bit of reminding of what we've been talking about. Now let's talk about the driven harmonic oscillator. So imagine, we have the same case. We separate these charges with an electric field and then shut off the electric field. But say maybe we turn it back on so that the electric field varies sinusoidally with time and applies a force F naught cosine omega t plus, just omega t. So it varies sinusoidally in time. Imagine the electric field produces this force on this oscillating dipole. Well then, this is going to change our equation here and make it what the mathematicians would say inhomogeneous. This is what it would look like. So all we would do is write this side on the, I forgot the t, write this side on the right, write this expression on the right hand side of the equation. And since it's easier to work with complex exponentials, we're just going to do this, but at the end we're going to get rid of the imaginary part. So e to the I omega t by Euler's formula is just a cosine part plus an imaginary sine part. So, now the mathematicians tell us that the solution to this so-called inhomogeneous second-order linear differential equation is, well, x of t, but it's a solution to the homogeneous part, which we've already found, the general solution to the homogeneous, which we'll call g of t, plus a particular solution, which we'll call P of t. A particular solution to this equation. Now, the equation that we found, well, I already set it up here. So basically I'm renaming this thing up here G of t. So what we want to do is find a particular solution that satisfies this equation here. To do that, we're going to try assuming, although we kind of are cheating because we already know what to assume, but usually exponentials are good things to assume. So we're going to assume P of t is of the form some constant a times e to the I omega t plus some phase factor phi. Let's call this phase factor something else, because it's not the same phase factor we encountered in the previous video. Okay, so let's differentiate P one time and then. Okay, so now we have everything and we can plug P into this equation instead of X. I should have mentioned here that our phase factor, delta, is going to end up being the difference in phases between, I don't know how to write that mathematically, but it'd be the difference in phase between the natural frequency for the system, omega naught, and our applied frequency to the system. So each of these frequencies will have a certain phase, and that phase difference is delta. Okay, so down here, all we did was plug in into this general equation here, and now what we're going to do is try to simplify things and solve to see what A is going to look like. So I'm going to flip the page and then rewrite this on the next page so we have to reference. Okay, so that's what we had. Now, to solve for A, here's going to be my strategy. I know I can split the exponentials up, and these exponentials over here will cancel this, and I'll only have the exponential with I times delta, and I can take all the A's out. So I'll have A over here, and I can divide by some stuff, and have that stuff in the denominator. And since I'll have an imaginary part only on one side, I'll rewrite the complex exponential in its real parts and its imaginary parts, and we'll see if that gets us anywhere. So I'll do that now. Okay, things are looking a little bit simpler. I'm going to divide by the mass because we have things like the natural frequency defined in terms of this K over the mass. If we recall, K over M was defined as omega naught squared. So I can rewrite that here, omega naught squared, and I'm going to recall this, I'm going to redefine this gamma over M. I'm going to call that capital gamma. Okay, so we're almost there. Let me rewrite this one. Okay, so we're almost there. What I did was just make this look a little nicer, and I rewrote the complex exponential as its cosine and sine parts. Now, we're going to equate the real part, and we're going to equate the imaginary part, and solve for the sines and the cosines. Okay, so we have an expression for the cosine and an expression for the sine. And now we're going to use the fact that sine squared x plus cosine squared x is equal to 1. Okay, so there we go. We have an expression for A. And now we can plug this in to our solution we assumed and see the result. So the solution that we assumed was, let's see, we assumed our particular solution P of t was equal to A times, let's see, e to the negative, no, there was no negative, it was I omega t plus phi. So we plug our A in, F naught over M, but we can rewrite this. We can just rewrite the real part, because I said I'm going to do that at the beginning. So just rewriting the real part of P of t, we get real part P of t is going to be equal to, A is going to stay the same, but we're just going to have a cosine of omega t plus phi. That's the real part of P of t. And remember, I said the general solution is going to be x of t equals g of t plus p of t, but in this case, I'm kind of calling these the same thing. So our g of t, I had written as c e to the negative gamma t over 2m cosine omega t plus did I start calling delta phi? Yes. I started calling delta phi here. Okay, so this is not phi, this is delta. Sorry about that. Okay, so this was phi. And this part was the A cosine part. So F naught over M. Omega naught squared minus omega squared, all that squared. Plus omega gamma squared to the half cosine omega t plus delta. Okay, so now this is our final solution. But there's some things to note. So note that as omega naught approaches omega from either the left or right, the second term blows up. And the first term basically doesn't matter. And now when that happens, there's a resonance effect, and you get resonance enhancement. So that means that this term barely even matters. Only this term matters because the denominator is going to be huge. And that's resonance enhancement. And if you scan different omegas, like a large range of omegas, because you control omega. Omega is the frequency of electric field that you apply to the system. So you scan that, and you see where you get a big peak. Well, that's all absorption spectroscopy is. It's the absorbance versus the frequency that you scan. So where that's the most intense, it's a characteristic of certain molecules. Molecules, atoms, any sort of dipoles, they're going to have a different natural frequency, and therefore, as you collect absorbance versus omega, you're going to have peaks in different spots. So that's why I think the driven harmonic oscillator is so important in spectroscopy. And you have to understand the driven harmonic oscillator to understand spectroscopy. So that's probably the most important note. Another note is that as t gets longer and longer and longer and approaches positive infinity, the second term dominates. So at large times, we don't have to worry about the first term so much because of the exponential envelope part. Because if you plug a large t into this, e to the minus a large number is going to give you a very, very small number. So the first term is going to be small, and the second term will be much larger relative to the first term. Now another thing, try to remember this particular solution, because in a future video, most likely, I'm probably going to discuss the Kramers-Heisenberg-Dirac equation, which is an expression for calculating the polarizability, and it looks very, very similar to this right here. The denominator is almost identical, but this F0 over m is some quantum mechanical bras and kets and those sorts of things. Although it's just a number. But there is a very important connection, which you usually don't encounter in textbooks, between the driven harmonic oscillator solution, mainly the second term, and the Kramers-Heisenberg-Dirac, or KHD, as it's usually called, expression. So, I might do a Mathematica supplement to this, if I can get a program like this to work. But besides that, I hope you guys enjoyed that, and have a great day.